But not all of them. Tables only go so far. And that is why I want to discuss with you two theorems which will help you to find moments of inertia in most cases. Suppose we have a rotating disk, and I will make you see the disk now with depth. So this is a disk, and we just discussed the rotation about the center of mass, and I call this axis L. And so it was rotating like this, and it was perpendicular to the disk. This is the moment of inertia. But now, I'm going to drill a hole here, and I have here an axis, L prime, which is parallel to that one. And I'm going to force this object to rotate about that axis. I can always do that. I can drill a hole, I can have an axle, nicely frictionless bearing, and I can force it to rotate about that. What now is the moment of inertia? If I know the moment of inertia, then I know how much rotational kinetic energy there is. That's 1/2 I omega squared. And now there is a theorem which I will not prove, but it's very easy to prove, and that is called the parallel axis theorem. And that says that the moment of inertia of rotation about L prime, provided that L prime is parallel to L, is the moment of inertia when the object rotates about an axis L through the center of mass plus the mass of the disk times the distance d squared. So this is the mass. And that's a very easy thing to apply, and that allows you now, in many cases, to find the moment of inertia in situations which are not very symmetric. Imagine that you had to do this mathematically, that you actually had to do an integration of all these elements mi from this point on. That would be a complete headache. In fact, I wouldn't even know how to do that. So it's great, once you have demonstrated, once you have proven that this parallel axis theorem works, then of course you can always use it to your advantage. Notice that the moment of inertia for rotation about this axis, which is not through the center of mass, is always larger than the one through the center. You see, you have this md squared. It's always larger. There is a second theorem, which sometimes comes in handy, and that only works when you deal with very thin objects. And that is called the perpendicular axis theorem. If you have some kind of a crazy object, which of course we will never give you, we always give you a square or we give you a disk, but it has to be a thin plate, otherwise the perpendicular axis theorem doesn't work. And suppose I'm rotating it about an axis perpendicular to the blackboard through that point. I call that the z-axis. It's sticking out to you. That's the positive z-axis. I can draw now any xy axis where I please at 90-degree angles, anywhere in the plane of the blackboard. So I pick one here, I call this x, and I pick one here, and I call that y. So z is pointing towards you. Remember, I always choose a positive right-handed coordinate system. My x cross y is always in the direction of z. I always do that. And so you see that here, x cross y equals z. Now you can rotate this thin plate about this axis. You can also rotate it about that axis. And you can also rotate it about the z-axis. And then the perpendicular axis theorem, which your book proves in just a few lines, tells you that the moment of inertia for rotation about this axis here is the same as the moment of inertia for rotation about x plus the moment of inertia for rotation about the axis y. And this allows you to sometimes, in combination with the parallel axis theorem, to find moments of inertia in case that you have thin plates which rotate about axes perpendicular to the plate, or sometimes not even perpendicular. Sometimes you can use, if you know this and you know this, then you can find that. So both are useful, and in assignment 7, I'll give you a simple problem so that you can apply the perpendicular axis theorem.